learn some things today. Oh, have you started the thing? Okay. Okay. We're going to learn about the speed of a wave on a string, and we're actually going to learn a formula for that and talk about how that pertains to tuning your guitar. And then we're going to talk about the speed of wave and various waves in various media, a gas, liquids, and solids. And then we're going to talk about the nature of sound, the fact that sound is a compression wave. Sound is a longitudinal wave where you get compression and rarefaction. That's the way sound works. But first, the speed of a wave on a string. I agree. The speed of a wave on a string depends on two things. Speed of a wave on a string depends on two things. I need someone to come up here and be my spring buddy. You, all right, come on up, Imani. Sweet. Imani, you are my spring buddy. Take that side. Okay. And get to where that Home Depot box is and try not to trip on anything. Okay, thanks, Imani. So here we go. You can see that we have this spring, and we're going to call it a string. It's essentially a one-dimensional object, more or less. Okay, and we can see how fast a wave travels from me to Imani, right? You can get the speed of that disturbance. Now, if I wanted to measure the speed of this disturbance, I could take my timer and go clicky, clicky, and then I could measure the distance between me and Imani and divide by that time. But is there a better way to do it than for me to go clicky, clicky, and then divide, my distance from Imani by that time? What would you recommend I do? Well, I certainly don't want to try to measure the time it takes for this pulse to get from me to Imani. That's a pretty quick time, and my reaction error is going to be significant. Instead of measuring that, what would you have me measure the time of? Say that again, Imani. Yeah, several cycles. Like this. What if I went this? Clicky. Clicky. Okay? Then the distance between me and Imani, how much would I have to multiply that by before I divide it by the time?
3.
Not 3. What's that? Here, watch again. Click. Okay, so it wasn't 3. How many Mr. Shana Imanis did I have, Noel? Yeah, 6. So just make sure when we do this lab, we're going to do a lab where you have to do this sort of thing. When you do it, remember to multiply the distance between Mr. Shana and Imani by 6 before you divide by that time. Okay, here's another question. You can see how fast this is moving, 1 and 2 and 3 and... Is there something I can do to the spring to make that wave move faster? What would you have me do to make that wave move faster? What's that? Oh, is that you, Imani? I heard a girl voice, and I'm looking, and I see nothing but boys except, listen, it wasn't her. Shorten the distance? Okay. So you mean like get closer to you like this? Okay, now watch the wave. Now watch the speed. Is that going faster or slower? That's going slower, right? I mean, I can just see visually. That's a lot slower than this, right? This is faster. So what if I wanted that pulse to go faster still? What should I do?
Increase the backup more.
What's that?
Increase the distance.
Say again.
Increase the distance.
Increase the distance, okay. Or how about if I kept the same distance? Why not just increase
Tension.
the tension? Yeah, so here we go. Hold on tight, because I'm going to increase the tension. Here we go. Now watch the speed. Is that faster?
Yeah.
Sure. Boom. So I just want you to see one thing that the speed of a wave depends on a string is the tension in the string. High tension, high speed. Low tension, low speed. And when I got close to Imani, that was super duper low tension, which gave me super duper low speed. But there's another thing the speed of a wave on a string depends on besides the tension. I'm going to demonstrate this by having the wave go from that spring to this cotton string. From that steel spring to this cotton string. Try saying that fast. Okay, move back to the cabinets. And I know the audience, the video audience isn't going to get a thing out of this, but we'll try. Okay, I want you to see, to compare the speed of the pulse that Amani's about to do, the speed of the pulse on the spring versus the speed of the pulse on the string. And before we go any further, is the tension on the string the same as the tension on the spring? Newton's third law, baby. Is the amount of force I'm exerting on Amani the same as the force Amani's exerting on me? Absolutely. Is the force that each molecule of the string exerting on each other the same as the force that each other is exerting on each other? Right. And then we get to the spring and nothing's changed. If I'm exerting 10 newtons of force on Amani, not only is she exerting 10 newtons of force on me, but every particle in the string and spring is exerting 10 newtons on its neighbor. You see? So yeah, the tension's the same everywhere. Okay, but I want you to see if you can't discern what the speed, the difference in the speeds are. So Amani, give me a pulse. Okay. I want you to notice you're able to follow the pulse pretty easily from Imani to the tie point. But can you also follow that pulse from the tie point to my hand? Here, do it again. Okay. Here, do it, and it's the first one that really matters. Do it one more time.
Yeah.
So tell me, where's the pulse moving faster?
String.
How many people say on the string?
Yeah.
Yeah, good for you guys. It's moving so fast, can you even see the pulse travel?
Barely.
No, the pulse hits that tie point and then the string just immediately bucks. I mean, that's the time it takes for the pulse to get from there to here is almost instantaneous, right? Whereas, I mean, here, watch this. You know, I can make a pulse and it goes from me to the tie point almost instantaneously, but then you can watch that pulse move from the tie point to Amani. See what I mean? So I hope you see that the pulse is moving a lot faster in the cotton string. Thanks a lot, Amani. Yay. Here, thank you for clapping. Okay. So what happened is the difference between the string, the cotton string, and that heavy steel spring is not the tension. They all have the same tension. The difference was the density, okay? And so that's the two things that the speed of a wave on a string depends on. The first thing is tension. Tension. Raise the tension, or maybe I'll say increase the tension. If you increase the tension, then what do you do to the speed of the disturbance? The pulse.
You increase the speed.
Yeah, increase it or raise the speed. Okay. The next thing it depends on is a quantity that I call linear density. I can't use normal density because that string is essentially a line. It's a one-dimensional figure, so I can't talk about cubic centimeters of string when it's just pretty much a one-dimensional figure. So I have to use linear density. And if I decrease the density, decrease the linear density by going from a steel spring to a cotton string, then what did I do to the speed of the wave? Did it get increased or decreased when I went from high density to low density? Yeah, it got increased. Raise the speed. So based on this, here comes the equation. If we had done a bunch of measurements, you would get, in fact, you're actually going to demonstrate this in the lab we're going to do. But the formula is this. Speed of wave on a string equals V, and that equals the square root of tension over mass over length. Where T equals tension, and that's measured in newtons. And M over L, mass per unit length, we call that the linear density. And the units of linear density is kilograms per meter. So let's go ahead and calculate the speed that the wave was moving on the string that Imani and I were holding. This is an example of the string, but it's just separated from the spring. This string, the length of this string ends up being approximately 2.2 meters. I'm now going to measure the mass of this string. I put it on the 3D balance, and the mass ends up being 73 grams, excuse me. So here comes example number 1. How much force were Imani and I exerting on each other? I estimate around 10 pounds, which is about 50 newtons. So I have a string. The mass of the string is 73 grams. The length of the string is 2.2 meters. The tension that Imani and I were exerting on each other is 50 newtons. Find the speed of the wave. Good luck. I'll give you a hint. Please plug into this formula. Anais, I hate to stress you out, but the exam, when are you going to take the exam?
Can I stay in your lunch?
Yeah, sure. But then what do you have 5th period?
I have English.
Is it AP English? Well, I mean, you're not going to be able to complete it during lunch. But we'll talk after class. Yes?
I can't do the
Sure.
first that in my head. Wait, I have my iPad.
You should grow your hair out. As long as mine.
You're crazy.
You may get into a ponytail.
I'm fine.
You cute little ponytail.
I'm fine.
You cute little ponytail.
I'm fine.
Come on.
No.
Ponytail. You see? Let me show you one.
Are you making sure that you convert the grams to kilograms?
Oh.
Oh, yeah.
Because if you're going to have newtons, you better have kilograms, MKS units, meters, kilograms, and
38
seconds.
meters per second. I don't know if that's right.
What'd you get?
38 meters per second.
How many people got 30? Anyone get 38.8?
Yeah.
Hey, good for you guys. That's what it is. Approximately 39 meters per second.
38.04.
Interesting.
So I want you to see, you had trouble seeing the motion of that wave on the string because that wave was going like, 85 or 90 miles an hour, So yeah, you're not going to see 85 or 90 miles an hour very well. And what made that go so fast is because the linear density of the string is so small. let me talk, how many people here actually play a stringed instrument like a guitar or a ukulele or a, okay, many of you, okay, good. So tell me, let's say a string is flat. That is a string, the frequency of sound emanating from the string is lower than it ought to be. What do you do to the string? Good, increase the tension, right? What is increasing, tighten it up. What does tightening the string up do to the velocity of the wave?
Increases velocity.
Yeah, increases the velocity. And if you increase the velocity, I just want to point out to you, V equals F lambda. It turns out we'll learn later that lambda, the wavelength of the standing wave, is determined by the length of the string. And you're not changing the length of the string. You got your nut, you got your bridge, and that's it. You're not changing the length of your string. But by tightening the string, you increase the velocity of the wave, which means you increase frequency. Hey, let me ask you another question. You've got high-pitched strings and low-pitched strings. Which are the fat ones, the high-pitched strings or the low-pitched strings? Good, the low-pitched strings. Why? Why are the low-pitched strings? Why is it that a high-pitched string, a high-frequency string looks like this, and a low-pitched string is a wire with another wire wrapped around it like this? Why do they do that?
Linear density.
What's that?
Linear density.
Yeah, what are they trying to do to the linear density here?
Increase the length.
Yeah, increase the linear density so that you decrease the velocity of the wave. Decrease the velocity of the wave, and you got a lower frequency. Has anyone ever seen an electric bass guitar?
Yeah.
What do those strings look like?
Fat.
Very, very thick, right? Very, very high linear density, because they need a very low velocity to get that really low frequency. Unless you want to play a bass guitar that's, 100 yards long, then you can get your low frequency with a string like this, Okay, that's the speed of a wave on a string. Let's talk about speed of sound in media. Speed of sound in media, different media, mediums.
So hot.
Huh?
So hot.
It's not that hot.
So hot.
It's not that hot.
Even Travis even hot.
Huh?
I was talking to Travis and he was like, that just got ridiculously hot.
I don't know what you're talking about. My mom drinks it hotter than I do.
That's what you get when you meet with metal chopsticks. That's what you get when you meet with
Okay.
metal chopsticks.
Speed of sound in air is approximately 340 meters per second. Okay, 700 something miles an hour. How about the speed of sound in water? The speed of sound in a liquid.
Slower.
Is it going to be slower or faster? How many people say slower? How many people say faster?
But we can say slower.
Okay. You say faster? Logan, why would you say faster?
Physics last year.
That's a good answer.
Cool. This, Logan's correct. It is faster. It's significant, 4 times faster. Now I'm asking why. Why would the speed of sound be so much faster in water than in air? Yes, Logan?
Because the density is like, there's more.
Okay. Here, let's look at air.
Good job, Megan.
Here's my air, and here's some air molecules. Okay? There's my air molecules. That's air. Let's go ahead and look at water. Okay, water. Here's water. It's amorphous. It's, it's not solid.
Takes on the ship's container.
Someone tell me, why would sound travel faster in water than in air? Yeah, I can see that there's more of them, that the molecules are closer together. How does that help me? Yes?
So
No?
there's more particles for it to bounce off of.
Okay, good. Here, let me give you a scenario. Remember I talked earlier about us all getting in a circle and holding hands?
Yeah.
And then I squeeze the hand and we see how fast that disturbance goes around? What if we did this? What if we said, rather than holding hands, because that's icky, we all stood about 2 meters away from each other? Now, how would that affect the speed if someone squeezes my hand and then I have to go step, step, squeeze? How's that going to affect the speed of the disturbance? Going to make it way slower, right? You guys okay with that? If these molecules have to, because you don't want the molecules to actually travel, you would prefer if the molecules were all holding hands. So all they have to do is go squeeze, right? Squeeze, 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 and then the disturbance propagates. But you don't get to have that with air. They don't get to go squeeze. They end up having to travel to hit the next air molecule. You see? Water, not so much. How about solid? Speed of sound in, how about steel? What do you think the speed of sound in steel is going to be?
Extremely unridiculous.
Okay, pretty darn fast, I think is a good way to put it. Approximately 6,000 meters per second. So my question to you now, what is it about steel that makes the speed of sound even faster in steel?
All the particles are compact together.
Good. All the particles are compact together. Here, I'm going to make steel. There's my steel. Not only are they compact, but tell me, what can you tell me about the strength of the bonds of steel versus water?
Stronger.
Yeah, very strong bonds. You can almost think of this as like having higher tension. The intermolecular forces are higher. They're stiffer, you know? Something that affects this guy is going to affect these guys more readily because they're bonded so tightly to each other. You see? So yeah, that's it. That's the difference in speed of sounds in air, water, and steel. You know? Okay. I think, what else did I want to talk about?
Nature of the sound.
Yeah, that's coming next. I thought there was something else I was going to tell you guys. Here, let me look at my thing. Sorry about that video audio. Oh, yeah.
Take notes.
Okay. Hey, let me tell you about something else.
Fine, I'll go hold Brianna's hand.
Stay away from that thing.
I'll hold Noelle's hand.
Stay away from that thing.
I'll hold Stan's hand.
Okay.
I'm actually kind of more okay with that.
Oh, here, I'll get over here. I am a man, and because I'm a man, I have a low-pitched voice, because manly men have low-pitched voices. Mine is not as low-pitched as my 16-year-old son's, but it's still reasonably low-pitched. Whereas someone like Anais has a high-pitched voice. You guys okay with that? So the frequency of her voice is significantly higher than the frequency of my voice. Does that mean that when she talks, it's going to take more or less time for me to hear her than for her to hear me? That is, does the frequency of our voices affect how fast sound travels through the air?
No? Question mark?
Well, let me ask this question a different way. A radio wave versus visible light. How would you compare the frequency of a radio wave versus the frequency of real light, of visible light? Yeah, lower, way lower. But you tell me, what speed does radio waves and visible light, what speed do they travel through air at?
Same one.
Yeah, the speed of light, right? So I want you to know something very important about waves. In a particular medium, all waves travel at the same speed. Doesn't matter what their frequency, wavelengths, or amplitudes are. All waves travel at the same speed for a given particular medium. Or maybe I should say, for any particular medium. waves travel at the same speed. Now, obviously, sound waves travel at a different speed than light waves. You got to compare apples with apples, you know? But definitely, because radio waves travel the same speed as light waves, which travel the same speed as X-rays, and we got V equals F lambda, and they all travel at the same speed. If I've got a wave with a higher frequency, what's going to happen to its wavelength?
Decrease.
Yeah, lower wavelength. So this radio wave might look like this, and this visible light wave might look like this. Right? They both got the same speed, in fact, the speed of light. Okay? But this guy's going to have a big wavelength and a low frequency, and this guy's going to have a small wavelength and a big frequency or a high frequency, you know? Because they're all traveling at the same speed. And that's true for any type of wave in any medium. You know, sound waves, they all travel at the same speed. So a high-pitched speaker is going to have a small wavelength. That's the first thing I need you to know. But there's a second thing I need you to know about waves conceptually. Has anyone ever gone to a pool party? Anyone ever gone to a party that has a swimming pool in it? Okay, and you know, at pool parties, usually they have incredibly loud, horrible music. You guys experience that?
Yeah.
Yeah. And now, have you ever gone underwater to hear the music? And of course, when you go underwater, the music might sound garbled, but does the frequency change? Does the pitch of the music change? When you go underwater, does Taylor Swift sound like Barry White? Does a saxophone solo, you go underwater, now it sounds like a flute solo?
No.
No, doesn't it sound pretty much the same? Does anyone, who knows who Barry White is? Yay! Oh my God, I love Barry White. He's a genius. Oh, well, don't get me started. I just love loved Barry White because he passed away. Yeah. Okay, well, the point I'm making is when a wave moves from one medium to another medium, it is the frequency that remains unchanged. Not the wavelength or the speed, it's the frequency. Let me show you why. Here, imagine this is your swimming pool, so that this is water and this is air. And you've got, just one second. You've got some sound coming to hit the water. You've got a sound wave. Now this is kind of, misleading because sound waves are longitudinal. They're not transverse, but it's hard for me to draw a longitudinal wave. So I'm going to draw a transverse wave for sound, even though we know sound is longitudinal. But the point I'm making is this sound wave is going to have high pressure, low pressure, high pressure, low pressure hitting this water. And so sound hitting the water is no different than my hand hitting the water. You know? Crest, trough, crest, trough, crest, trough, crest, trough, crest, trough, crest, trough. Okay? I'm slapping the water. Well, if I'm slapping the water with the same frequency as the sound, do you see that that wave is going to propagate through the water at that same frequency? If I'm going slap, 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 then the waves going through the water are going to have the frequency, slap, 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 slap. Does that make sense to you guys?
Yes.
So now I need to put that in words. When a wave goes from one medium to a different medium, the frequency remains unchanged. When a wave passes from one medium to a different medium, the frequency remains unchanged. Consider a light. It is the frequency of light that gives it its color. The frequency of light gives it, in the same way that the frequency of a sound wave gives it its pitch, the frequency of the light gives it its color. Have you ever had a situation where you got a red light and you shined it through a transparent glass and it came out blue or green? Yeah, no way, right? That's because this red light passing through a transparent medium is not going to stop being red. It's going to be red no matter what media that red light passes through, because the frequency is not changing. The only way you can change the color of light would be to pass it through media that absorb some of the colors of your light. Like if you had white light and you put it through some medium that absorbs green and blue, well, now that white light's going to emerge red, okay, because you just removed the green and the blue from the light. You know what I mean? But if you're putting light through a transparent medium, a clear glass, it's not going to change its frequency. So how about this? V equals F lambda. Now I've given you a situation where the frequency is remaining unchanged. So I'm going from air, whose velocity is 340 meters per second, to water, where the velocity of a sound wave is going to be 1,500 meters per second. I'm going to greatly raise the velocity of the wave. What's going to happen to the wavelength? Is it going to increase or decrease? Hope you're seeing if this guy's going to rise and this guy's going to remain the same, and this equality to stay an equality, this guy's going to have to rise as well. Right? If you increase this guy and keep that guy the same, that guy's going to have to increase. Right? Just think about it. And so when this wave passes into the water, suddenly it's going to have a much bigger wavelength because it's going so much faster. You see? But the frequency remains the same when you go from one medium to a different medium. Alrighty. Well then, here's the last thing I want to talk about, the nature of sound. Sound is a longitudinal wave. This is a speaker. This is a type of speaker that's in your cell phone or wherever. This is like a big stereo speaker. All a speaker is just a cone, and the cone vibrates. This cone just pushes air and then pulls back, and then pushes and pulls back, and it just vibrates back and forth. And by compressing and decompressing the air, you get your sound. So at times when the speaker shifts to the right, you get compression. Then when the speaker pulls back, you get low pressure, you get rarefaction. And by the speaker alternatingly compressing and pulling back, pushing forward and pulling back, you get these regions of compression, which is high pressure, like there, there, and there, and there, alternating with regions of a rarefaction or rarefied air. Rarefied air, I don't know why they use, I guess, compression and rarefaction. Compression and rarefied. But anyway, that's low pressure. And that's going to be these regions here. So here's your human being. And this is his ear.
Oh,
And you know, you actually have an ear canal. And then you have your, what comes at the end of the ear canal? Yeah, you got your eardrum. And then you got your inner ear. Okay? In your inner ear, the pressure in your inner ear is whatever it was the last time you popped your ears. So you got pressure in the inner ear. You got pressure in the outer ear that's changing. And so you've got this sound that's coming to your outer ear. These alternating regions of compression and rarefaction. Like the sound I'm generating right now. And so you get this high pressure region at the entrance of your ear. The pressure on the other side of your eardrum is 1 atmosphere. This is high pressure. Which way is your eardrum going to deform? Does it go that way or does it go that way? If you got high pressure here and 1 atmosphere, just normal pressure there. Hope you see that it's going to go like that. It's going to be pushed in. And then, you know, a moment later, you've got this rarefaction, low pressure, which means the eardrum, since it's got 1 atmosphere on one side and a low pressure region on the other, it's now going to go boop. And it'll go boop, 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 alternating, and it vibrates the eardrum. And whatever the frequency of these alternating high and low pressure regions are, that's the frequency that your eardrum vibrates at. And those vibrations excite cilia inside your inner ear, and then you hear sounds, and you hear my irritating voice. Alrighty. Well, hey, what did we learn? We learned the speed of a wave on a string depends on tension and the linear density of the string, and you learned a swell formula. We learned why the speed of sound goes fast, faster, fastest in air, liquid, and solid. And we talked about the frequency and stuff, wavelengths, and it's all good. So have a good day, though.